Yeah. So optical isomerism, you find it in compounds that do not have a plane of symmetry. How does this look like? Like for like tetrahedral structures may, what this is what you're familiar with, right? So suppose tetrahedral structure hai. If any two groups bonded on two sides are the same, something like this, then we have a plane of symmetry here, like A and A is like right here. They are symmetrical with each other. But if all four groups that are bonded are completely different from each other, we have suppose A, B, C, D, then this does not have a plane of symmetry. This particular compound does not have a plane of symmetry. Now, what is important with plane of symmetry is that because you don't have a plane of symmetry, this gives rise to two non-superimposable mirror images. Okay. So if I take the mirror image of this, I'm going to modify this only. So if I take the mirror image of this, so I'm going to get A over here, B over here, C over here, and D over here. And if I try, like if I pick this up and put it over here, they will, like, I can't like the two molecules will not coincide with one another. So that's what it means by non-superimposable. Like if I take this, put its mirror image against it, extra bits are peeking out over here, right? So they are not superimposable with each other. The mirror images are not superimposable over one another. So whenever this happens, you say that there is a chiral center. So this phenomenon, this is called chirality. So just like in organic chemistry, either be optical isomerism mein, you have chirality coming into picture. And these two forms, the two mirror images that we get, they are called dextro and levo, same names as that. So you have dextro denoted by D and levo denoted by L. So the speciality about both of these, like why do we care about this, is they rotate polarized light in different directions. Okay, so dextro molecules, like if we say it's dextro rotatory, it means that the rotation is to the right, and levo rotatory means the rotation is to the left. So what do you mean right left? If you have a beaker of this, if you a beam, like if you make polarized light pass through it, if it is dextro rotatory, it will rotate to the right. If it is levo rotatory, it will rotate to the left. And this pair of right and left, like this pair of dextro and levo forms, they are called enantiomers. So this pair of the two non-superimposable mirror images, this pair is called, or they are called, it's like a pair of, you call them a pair of enantiomers. So the terms, concepts, definitions, everything is exactly the same as what you have in organic chemistry. This is the chiral center. Whenever this comes up, you call it, that's the point of chirality. It's chirality whenever you have two non-superimposable mirror images. Out of the two, one is a dextro-rotatory form and one is a levo-rotatory form. And the pair of dextro and levo-rotatory, they are called enantiomers. So optical isomers are also called enantiomers. And how do you differentiate between dextro and levo-rotatory? One is like the basis by the structure, but the main point of difference between them is the fact that one form rotates polarized light in one direction, and the other one rotates it in a completely the opposite direction. So if it rotates it to the right, you call it the dextro form, and if it rotates to the left, you call it the levo form. Okay. And of course, 50-50, like a 50% mixture of both. Do you remember this, what it is called? If you take 50% of one, 50% of the other, what is it called? Racemic mixture. Okay. So these are all like the concept and the terms related to it. Let me know when you've finished noting all these down, and then we'll move on to specific cases like examples.
Ma'am, I'm done writing.
Okay, cool. All right. So the first case, so we'll be looking at exclusively octahedral structures in this particular case. So suppose it is of the type, like if the coordinate is of the form MAA3. So we like denoting it as AA, matlab it's a single ligand, but since there's two of them, meaning it's a didentate ligand. Okay. So for example, if you're talking about cobalt oxalate, if you if you don't remember, oxalate is like anion of oxalic acid. This is what it looks like, COO minus, COO minus. So these are the two places where it can link. So this is what its structures look like. So cobalt is at the center. We have three oxalate atoms. Each of them have two. Matlab they form octahedral this thing. So you have one on top, one on the bottom, and four of them on the plane, square planar. So you have one oxalate like this, one oxalate over here linking these two, and the third one is over here linking these two. So iska mirror image, this is a mirror. You have cobalt, same octahedral. So this one is on this particular plane. Iska mirror looks like this. So is on top. This is on the bottom. Okay. So this is roughly what it kind of looks like. So it is difficult to figure that these two are non-superimposable right now because we are drawing it on a 2D plane, right? Yeah. So I found like a 3D structure simulation on a website. So once you finish noting down the structure, I'll switch to that screen. This is one example. You can also note down another example if you want. Another one is same thing, cobalt, but ethylene diamine taken thrice, EN3. Follows the same principles. Ethylene diamine also, like it's a didentate ligand. So the structure will essentially be the same, just that the specific atoms making up the structure will be different. Let's make it a little more. So this is the plane. It's all in the same plane. This is on top and bottom. Maybe this is all on the same plane. Top and bottom. Okay, so one oxalate is on this particular plane, and two of them are like perpendicular to this plane diagonally. So we can imagine that one on top and one on bottom. Okay. Yeah, Sanskriti, let me know once you've finished. Okay.
Yes, ma'am, I'm done.
Okay. Finish the screen. Yeah. So it's not the exact same example. In this case, they've taken like tris diamine ethylene, like tris ethylene diamine ruthenium, wala this thing. So yeah, so these are the mirror images. So this is the 3D structure. You can see that the green color central atom, metal atom here, ruthenium. And how, okay, so if we were to like whatever you have noted down in your book, if I were to do it exactly like that, so यहाँ पे one structure that is there, let me just reload. Yeah, so this thing, it's in the same plane, like this is forming one part of the, like this is on the flat surface on the same plane here. And then this is over, like the other two EN structures, ethylene diamine structures are, so one is on top यहाँ पे and one is like going below the flat plane. And iska mirror image is exactly like this. Now, if I take one of this and put it over here, like even if I change this way, how is this gonna make sense? Just a second, guys. Okay, sorry about that interruption. So we're talking about, yeah, enantiomers. How will this make sense? Okay, so okay, just imagine if I turn this molecule by 180 degrees. So I'll get cobalt is plane, like in the horizontal plane, we have one oxalate molecule. Now this one only I'm turning it around this way, right? So whatever is behind, this is going to come in front. So whatever is in front, yahan pe, or let me just color code it. That'll make it easier. This is the green bit. And this will be the red bit. Okay. Smira, are you there?
Yes, ma'am.
So I am turning this by 180 degrees so that this flat structure comes on this side so that it's like matching this, the mirror image. Okay. So the blue color ka oxalate part, which is flat, is going to come over here. Now, the green one is on top, like this one is linked to the structure on top. So I'll keep the green on top. But when I turn it 180 degrees, jo piche tha, something that's like something was pointing towards, like, okay, on the screen it's pointing backwards, right? When I rotate it by 180 degrees, it's going to point on the front, right? So if I draw that, it's going to point on this side. So this oxalate's going to come over here. And then the red, which is on the front, is going to go back. So it's going to be over here. And then it's on the bottom. So this becomes like this. Iske piche. Are you able to imagine it? Like, does this make sense? ये नीचे की तरफ, नीचे और पीछे. Now, if I compare it with this, let me color code this to the mirror image structure. So the red part is facing this way. It's on the bottom. And the green part is on top and facing piche this way. Okay. So if you compare this one and this one, you can see that the places have been changed. Like the places of the individual ligands, like of the oxalate ligands, are interchanged. Yahan pe the green color oxalate ligand is facing the back side, and yahan pe it's facing the front side, is particular position mein hai. Okay. So you can't superimpose these two here, which is how we can say that they are two completely different molecules. Like that is the reason they are enantiomers. They are not like the same molecule. They're isomers. Okay. Yeah. Sanskriti Smera, is this making sense? You able to imagine this?
Yes, ma'am.
Yes, ma'am.
I'm gonna remove the black so that like let's keep the colors so that that clarity is there. So the green part has come forward. यहाँ पे जो पीछे था.
So, but to prove this irrationalized wonder equation, like if we don't rationalize it and can we put an equation and can we do that way?
Sorry, I
Yes,
was
ma'am.
not able to follow you. What did you say?
Ma'am, I didn't say anything. It was Samruddhi. Her class was going on.
Acha, it was her voice. Okay, okay. Okay. All right, but like, does this kind of make sense, you guys? Yeah. Okay. So I would suggest draw it yourself, like color coded. Imagine, turning it so that then it kind of makes sense a little bit. Okay. So this is one. And the rest of it, like the logic is the same. I'll just give you guys the format for the other octahedral system. This is one. The next is like, okay, you have three same didentate. The other format is if you have like complexes of the form M, AA2, X2. So in this particular situation, whether it's X2 or M, AA2, XY, in both these cases, only the cis isomer will show enantiomer, optical isomerism. Because the trans isomer, you have symmetry there, you have the plane of symmetry coming up. So only the cis isomer is the one that's going to show this. So इसका example, so cobalt En2 Cl2, for example. I'll have to flip the page to give the structures for this. Let me know once you're done.
Done, ma'am.
Okay. So here also cobalt is the central atom. Let's color code here also, make it get easier. Square planar, like the planar one, you have in the front one En, didentate here. The second En, let's say it's here, front side, and then the two here. Yeah. This is the mirror. Cobalt is in the center. This is का mirror image. So we have one EN. Let's solidify this in the front. The two chlorine is in the back, Cl, and one on top. And then the other EN, this is in the front again, and the bottom. Smira, I know you draw. Sanskriti, what about you? Do you do art, painting, sketching?
No, ma'am.
No? Okay.
I
That's
have a math exam on Friday.
okay. So Smera, like when you do drawing, you must have like have you worked with doing 3D perspectives and all of that? No? Okay. Got it. That probably would have helped like visualizing perspectives, foreshortening and all that. So.
Ma'am, maths में we had 3D वाला chapter, so उसमें we did make 3D boxes, but that is all I know.
Like, but that's like very like on the basic level, right? Like the introduction to 3D types. Okay. All right, so this is one type. And then the third type, suppose you have something, you just have one dientate ligand, MAA, then X2, Y2. So,
Ma'am,
hmm?
any reason for there not to be in the trans isomer in the pre?
Sorry, can you repeat that? I lost your voice for a bit there.
I was asking, is there any reason why we can't have any trans isomer in the previous one? Like,
In this case,
yeah, like EN like that, and then Cl.
so for like, will you see the main point about optical isomerism is that you should not have a plane of symmetry. इसलिए वो chirality will be formed. So once you get a trans isomer, this it's going to be symmetrical, right? It's not, you won't have that point of chirality there. इसलिए we specified only cis isomers.
Understood.
Right. इसमें an example again, we just take cobalt. So NH3 taken twice, Cl2, En. Sorry, so this will be neutral. Plus 2 minus 2. Here. So this is another example. Draw the symmetrical, like draw the mirror images for this. Like that's going to be your homework. Draw it yourself, attempt it. That way at least you'll, look at it, think about it, figure it out. Do it yourself. Okay. So
Ma'am, one doubt. So it will not be an example of isomerism, but the compound will exist, right?
the
In the
compound,
trans-
yeah, absolutely, obviously. So that's a very good case. So this would be an example of a compound that shows both types of stereoisomerism. So with cis trans you have geometrical isomerism, and the cis isomer by itself shows stereoisomerism with the, because of the chirality that it has. That's a good point. Okay. All right. So okay, you guys want to take like a 5-minute break before we start the next topic, because next it's going to be a little heavy. We'll get into the structure, VBT and CFT for coordinate compounds. Okay, so just revise up, like take about 5 minutes break. It's 5:33 now. Join back by 5:40. Okay, so join back at 5:40. So then we'll start off with VBT and CFT, then be done with the chapter.